In a substation control room, three primary components demand our attention: the SCADA workstation, the external transformer, and the Automatic Voltage Regulator, or AVR, relay panel. Our objective is the complete commissioning of the AVR to guarantee safe, automated voltage control across the grid. Before touching the equipment, we must establish the governance rule for this procedure. When standards from the IEC, IEEE, NEMA, or the manufacturer's own specifications disagree, you must always apply and document the most stringent requirement. Physical prerequisites come first, beginning with a comprehensive visual inspection as dictated by standard operating procedures. Next is a strict signal readiness audit. You must confirm that all baseline tests for the potential transformers and current transformers are signed off. With those confirmed, execute the phasing tests to establish a verified baseline sequence from the PT and CT secondaries directly to the AVR. Finally, enforce the mandatory lockout-tagout, carefully executing a strict 5-step safety isolation protocol before making any live equipment connections. Establishing this boundary ensures that secondary simulations remain isolated from the primary system, preventing unintended control commands or backfeeding during the test sequence. The first procedural module focuses on verifying the control panel scheme, the tap position, and SCADA feedback. We begin by checking the alignment between the remote tap position indicator, the local tap indicator, and the SCADA feedback screen. For any given transformer tap position, the values at these three separate locations must match perfectly. Next, we test the logic interlocks by initiating raise and lower commands. You must test these commands across all permutations of the local remote and auto manual selector switches to verify they only execute in their intended modes. During these tests, confirm that command paths are blocked if the automatic voltage control delay time is set shorter than the tap changer step time. Then validate the alarm matrix. We do this by simulating on-load tap changer, or OLTC, alarms. Track each simulated alarm, such as an AC/DC fail or a book hold trip, directly to the SCADA system to verify accurate remote feedback. Failing to clear these interlock hold points risks causing an immediate transformer out-of-step condition, which would render subsequent relay logic testing ineffective. Moving to the second module, we isolate the relay and execute secondary injection tests to verify bandwidth and timers. This diagram maps the required test kit connections. You connect the secondary voltage and current injection circuits to the relay entirely through the designated test blocks, isolating the device without disturbing in-service wiring. From here, map the digital inputs and outputs, confirming that all binary contacts and LED descriptions match the approved logic schematic. Initiate the bandwidth checks by injecting precise secondary voltage values into the relay. Based on those injected values, calculate the expected primary raise and lower boundaries. Compare those expected calculations against the actual measured values. The component must operate within a strict 0.4% accuracy tolerance. Next, we test the inverse timer, or T1 function. This graph plots the exact T1 curve operation, utilizing secondary voltage deviation. The curve is calculated using this formula: 30 multiplied by the given time factor times the bandwidth percentage divided by the voltage deviation percentage. Record the measured curve operating times against this formula across all the required time factors listed in the test form. Then transition to testing the definite timer, or T2, operating times by performing further secondary voltage injections based on the device's required settings. Finally, measure the exact command latency for the runback voltage settings. This strict accuracy, paired with verified inverse timing, ensures the AVR responds only to sustained voltage deviations, preventing unnecessary mechanical wear on the tap changer. The third module validates the blocking protection functions. This schematic details the required injection kit connections to the binary inputs. First, inject dropping secondary voltages to simulate a grid sag and trigger the under-voltage block. You must record the exact percentage pickup value at the precise moment the relay physically blocks the raise and lower tap commands. Next, inject excess voltage to cross the upper limit, confirming it triggers the overvoltage alarm. Then, inject current exceeding the nominal limit to verify that the overcurrent block completely disables the motor drive. With the standard blocks verified, use secondary injection to test the specific out-of-voltage timers. You also need to measure the duration of the automated raise and lower command pulses down to the millisecond. These blocking features override standard bandwidth logic to halt all tap change operations when the grid experiences voltages or currents outside of safe operating parameters. The final execution module focuses on voltmeter scaling and phase verification. This is the diagram for the secondary injection and switch function tests. Begin by cycling the selector switch and test switch through all phase states to verify correct channel mapping. Next, inject a specific percentage of the nominal secondary voltage into the panel. As shown in this equation, you calculate the expected primary voltage by multiplying that injected percentage by the nominal primary voltage. Verify that your calculated primary voltage exactly matches the actual number displayed on the physical digital meter. While cycling through, check for any display flicker or wiring phase mismatches across all selected channels. Perfectly timed relay logic means little if the control room cannot accurately monitor the true primary scale voltage via the panel. Even with strict procedures, field discrepancies occur. The most common is a bandwidth tolerance failure. If the device fails the 0.4% accuracy check, immediately verify the injection kit's calibration status and inspect the test block for contact resistance. If the physical connections are sound, troubleshoot the relay setting files to check for a firmware mismatch. If SCADA alarms are missing, trace the binary output mapping through the remote terminal unit point list to isolate the break in communication. Once tests are complete, you must remove all temporary injection leads and restore the test blocks to their normal operating positions. Ensure absolutely no testing equipment remains connected to the system, and the panel is physically secured before moving forward. Audit the final evidence package required for sign-off. This includes phase records, timer tables, run-back data, and SCADA screenshots. Before releasing the final hold point, confirm that absolutely no standing alarms remain active on the panel. Following this sequence ensures the AVR is accurately configured to maintain voltage stability and respond predictably to grid conditions once energized.